Tonight, we're going to explore something that sounds like science fiction, but happened in our reality just recently. A planet with a 99.7% chance of harboring life. You've probably seen the headlines. The James Webb Space Telescope made this discovery, and it's been circulating through science channels and news feeds for weeks now. But here's what most people don't realize. This isn't just another exoplanet discovery in a long list of distant worlds. This specific percentage, this particular reading, represents something we've never actually encountered before in the search for life beyond Earth. And by the end of this journey, you're going to understand exactly what that 99.7% probability really means and why it's forcing scientists to reconsider how we define a living world. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. The light we're analyzing from K218b began its journey 124 years ago. That's not ancient history on cosmic scales. That's recent. That's your great-grandparents' time. When those photons left that planet, it was 1900 on Earth. The Wright brothers hadn't flown yet. World War I hadn't started. Penicillin didn't exist. The oldest person alive today hadn't been born. And here's what that means. The photons hitting the James Webb Telescope right now left K218b before your grandparents were born. You're not looking at a planet. You're looking at a message in a bottle that's been drifting through the void since the Wright brothers first learned to fly. And if there's life in that message, if something was alive when it was sent, it's been living this entire time, completely unaware we're about to read its signature. This is the part that gets me. Not just that we might find life, but that the life has been there, doing its thing, while the news crawled across space at the fastest speed possible. It's already happened. We're just catching up. K218b sits in the constellation Leo. You can see Leo from Earth on any clear spring night. The star itself requires a telescope. Nothing special to look at, just another point of light. But that light has been traveling for more than a century before it reaches your eye. Think about what 124 years means in practical terms. If your great-great-great-grandparent looked up at K218b's star the exact moment a phytoplankton bloom released dimethyl sulfide into that planet's atmosphere, you're only now receiving that message. 4 or 5 generations of your family lived and died while those photons crossed the gap. The molecule itself, the actual chemical signature we're detecting, took seconds to rise from ocean to sky on K218b. Seconds. Maybe minutes if we're being generous. The light carrying news of that molecule to Earth took 124 years. That's the disconnect. The event was instantaneous. The report took longer than countries have existed. Here's the surprise most people miss. The light arriving tonight isn't showing us K218b right now. It's showing us K218b in 1900. We're looking at history, not the present. If there's life on that planet, we have no idea what it's doing today. It could have evolved into something unrecognizable. It could have developed technology. It could have gone extinct decades ago, and we won't know until another century passes. We're seeing a snapshot from the past, a very recent past by cosmic standards, but still the past. The present moment on K218b is invisible to us. It won't be visible until the year 2148. Every observation we make works this way. When you look at Mars, you're seeing it as it was minutes ago. The Sun appears as it was 8 minutes ago. The nearest star, beyond our Sun, shows itself as it was 4 years ago. Distance in space equals distance in time. They're the same thing. But 124 years hits differently. That's not abstract. That's within living memory of our species. Your great-grandmother could have been alive when this light began its journey. Maybe not your direct ancestor, but someone's great-grandmother, someone real. And if there was life on K218b in 1900, it's been reproducing this entire time, dying, evolving, going through 124 years of whatever passes for existence on that world. While we waited for the photons to arrive, the light left, it traveled. We finally caught it, And in that gap, entire generations of potential alien life lived out their spans. They had no idea we were waiting to hear from them. They have no idea right now that we just did. So when we talk about detecting life on K2-18b, we need to be precise about what that means. We're detecting evidence of life as it existed in 1900. We're reading mail that's been in transit for longer than anyone alive has existed. The sender might not even be there anymore. That's what makes this discovery strange in a way that's hard to articulate. We're not discovering life in the present tense. We're discovering that life existed, past tense, 124 years ago, and we're making educated guesses about whether it's still there now, in a present moment we cannot see. The universe doesn't offer us real-time information. It offers us history lessons. Every observation is archaeology. Every telescope is a time machine pointed backward, which brings us to the obvious question. What exactly are we looking at? What is this planet? This historical snapshot showing us K2-18b is about 2.6 times Earth's radius. That means if Earth were a basketball, K2-18b would be a yoga ball. Not enormous by planetary standards, but big enough that standing on its surface, if you could stand on its surface, would feel different. The horizon would curve away faster. The sky would seem wider. Everything would have more weight. The planet has 8.6 times Earth's mass. Mass is different from size. You can have a puffy planet that's big but light, or a dense planet that's small but heavy. K2-18b sits somewhere in between. It's larger than Earth and considerably heavier, which tells us something about what it's made of. Not a gas giant, not a rocky ball like Mars, something else. A category we didn't know existed until we started finding planets around other stars. The planet orbits its star every 33 days. That's a year on K2-18b, 33 days. One complete trip around its sun, start to finish, in less time than a human pregnancy. Think about everything that happens in a month here on Earth. You pay rent once. The moon goes through its phases. Maybe you finish a book or start a new habit. On K2-18b, that's an entire year. The planet completes its journey, returns to where it started, and the cycle begins again. If you lived there and celebrated your birthday every orbit, you'd have 11 birthdays in a single Earth year. By age 10, you'd be ancient, over 100 K2-18b years old. Your first decade would contain more New Year's celebrations than most humans experience in a lifetime. Seasons, if they exist at all, would flip faster than a monthly rent payment. Spring to summer, to fall to winter, and back again, all in 33 days. You couldn't plant crops the way we do. You couldn't track time the way we do. The rhythm of life would have to adapt to a calendar that moves like a metronome. The planet orbits at a distance of only 13 million miles from its star. For comparison, Mercury, the closest planet to our Sun, orbits at 36 million miles. K2-18b is nearly 3 times closer to its star than Mercury is to ours. It's hugging its Sun, racing around it at a speed that would make our solar system's inner planets look sluggish. Here's where it gets strange. Despite that proximity, K2-18b isn't a scorched wasteland. It's not boiling. It might actually have liquid water on its surface. Oceans, even. The planet sits closer to its sun than Mercury does to ours, yet it might be cooler than a summer day in Death Valley. We're trained to think close to star equals hot. It's intuitive. Mercury is close, and it's an oven. Venus is a little farther, and it's still hellish. Earth is farther still, and we have liquid water. The pattern seems obvious, but the pattern breaks when you change the type of star. K2-18b orbits a red dwarf. Red dwarfs are the runts of the stellar world. Small, dim, cool. Our sun is a furnace compared to them. If you swapped our sun for a red dwarf and kept Earth in the same orbit, we'd freeze solid. The oceans would lock up into ice. The atmosphere would collapse. You could have a planet sitting in Mercury's orbit around a red dwarf, and it would be a frozen rock. Distance matters less than we think. The type of star matters more. That's the counterintuitive reality of K2-18b. It's close, but not hot. It's fast, but not chaotic. It orbits a star so cool that being 13 million miles away puts it in what we call the habitable zone, the Goldilocks region. Not too hot, not too cold, just right for liquid water. Just right, maybe, for life. A year that lasts 33 days. A star that's cool enough to allow oceans at a distance where mercury would melt. A world that defies the simple rules we learned from our own solar system. That's what sent the light. That's the planet we're looking at through 124 years of travel time. Which raises the next question. What did the telescope actually see when it looked at this strange, fast-orbiting world? The telescope saw something that shouldn't exist. Dimethyl sulfide. 3 words that might just change everything we thought we knew about our place in the cosmos. The James Webb Space Telescope detected this molecule in the atmosphere of K2-18b at concentrations exceeding 10 parts per million. That's the chemical signature. That's what traveled 124 light-years to reach us. And here's why that matters. On Earth, dimethyl sulfide is produced exclusively by living organisms. Not sometimes. Not usually. Exclusively. There is no known non-biological process that creates dimethyl sulfide in significant quantities. Phytoplankton in the ocean are the primary source. Microscopic organisms floating in seawater, converting sunlight into energy, releasing this sulfur compound as a byproduct of their metabolism. Some bacteria produce it too. All living, all biological, every single source we've ever found. The molecule exists because life exists. Remove life from Earth and dimethyl sulfide vanishes from our atmosphere within years. It's not stable. It breaks down quickly in sunlight. The only reason we have any is because living things keep making more. The telescope also detected methane and carbon dioxide on K2-18b. Both of those can be produced by life or non-life processes. Volcanoes make carbon dioxide. Geological activity can generate methane. They're ambiguous. They tell us something, but not enough. But dimethyl sulfide is different. It's the smoking gun. 10 parts per million sounds tiny until you realize that's the same concentration as 1 drop of ink in a bathtub. 1 drop, dispersed through all that water. And we detected that drop from 124 light-years away. Think about the precision required for that detection. The light passes through K2-18b's atmosphere during transit. The star's light filters through those gases for just a few hours every 33 days. The molecules absorb specific wavelengths. The telescope catches what's left, and from that faint signal, that whisper of missing light, we can identify individual compounds floating in an alien sky. The light from K2-18b's star left during the Renaissance. Da Vinci was painting the Mona Lisa when those photons began their journey. They crossed the void for 5 centuries. They carried information encoded in their wavelengths, information about molecules that, on Earth, only life produces. And we caught them. We decoded them. We read the message. If you stood on K2-18b and looked up at its red dwarf sun, it would appear 6 times wider than our sun appears from Earth. A giant ember in the sky, glowing dull red, bathing everything in crimson light. The landscape would look alien, not just because of the terrain, but because of the color. Red shadows, red oceans, if they exist, red clouds. A world lit by firelight, day and night, forever. And in that world's atmosphere, something is making dimethyl sulfide. Here's the part that gets me. Dimethyl sulfide smells terrible to humans. Like rotting seaweed, like low tide on a hot day, like decay. It's the compound that makes beaches smell bad in summer when algae wash ashore and decompose in the sun. That distinctive, unpleasant odor of organic matter breaking down. The most profound discovery in human history, the confirmation that we are not alone in the universe, might literally smell like garbage. The chemical signature of alien life isn't some exotic molecule we've never encountered. It's the same stuff that makes you wrinkle your nose when you walk past a tidal pool. The universe's way of announcing itself is through the scent of decomposition. There's something almost funny about that. We imagined first contact 1,000 different ways. Radio signals carrying mathematical proofs. megastructures around distant stars, ships appearing in our skies. We never imagined it would smell like a beach at low tide, but that's what we're looking at, the chemical fingerprint of life, and it reeks. It reeks of the ocean. It reeks of biology. It reeks of processes we recognize because we swim in the same oceans where these compounds are made every single day. Do you understand what this means? We pointed a telescope at a planet orbiting a red dwarf star 8 times smaller than our Sun. A planet we can't see directly. A planet we only know exists because it makes its star dim slightly every 33 days. We analyzed starlight filtered through its atmosphere during those brief transits, and we found a molecule that, as far as every scientist on Earth can determine, requires life to exist. Not metaphorical life, not theoretical life. Life as we understand it. Life that metabolizes. Life that converts energy. Life that exhales molecules into an atmosphere. The detection is real. The molecule is there. The concentration is high enough that we can measure it with confidence. 10 parts per million isn't a trace reading that could be instrument noise. It's a clear signal. It's present. It's persistent. And it's waiting for an explanation. On Earth, that explanation is life, 100% of the time. Every source, every sample, every measurement, life makes dimethyl sulfide, and nothing else does. We've looked for non-biological sources. We've studied volcanic emissions, geothermal processes, atmospheric chemistry, photochemical reactions. Nothing produces it in the quantities we're detecting on K2-18b. Nothing that doesn't involve biology. So either there's life on that planet, or there's a chemical process no one on Earth has ever documented. A process that doesn't happen here. A process that violates everything we know about sulfur chemistry in planetary atmospheres. Both possibilities are extraordinary. One of them rewrites the story of life in the universe. The other rewrites chemistry. The light that carried this information left when Copernicus was proposing that Earth orbits the Sun, when we were just beginning to understand our own place in the solar system. That light traveled through expanding space for 500 years while we invented telescopes, discovered other planets, launched spacecraft, built instruments sensitive enough to catch single photons from alien worlds. And when we finally had the technology to read what that light was telling us, it said dimethyl sulfide. It said, something is alive. That's where we are. That's what the telescope found. A molecule that shouldn't be there unless something is making it. And the only things we know that make it are alive. But there's another possibility, one that scientists are racing to explore. That other possibility is this. We're wrong. Not wrong about detecting dimethyl sulfide. Wrong about what it means. Wrong about how confident we should be. The telescope detected DMS at what scientists call 3 sigma certainty. 3 sigma means 99.7% confidence. That sounds definitive. That sounds like we found it. But 99.7% confidence means that 3 out of every 1,000 times you run this measurement, you'd be completely wrong. 3 times in 1,000, the signal you're seeing isn't real. It's noise. It's an artifact. It's the universe playing tricks on your instruments. 3 in 1,000 doesn't sound so definitive anymore. The scientific standard for announcing a discovery isn't 3 sigma. It's 5 sigma. 5 sigma certainty means 99.99994% confidence. That's a 1 in 3.5 million chance of being wrong, not 3 in 1,000. 1 in 3.5 million. It's the difference between being right 997 times out of 1,000 and being right 3.5 million times out of 3.5 million tries. Like flipping a coin 22 times and getting heads every single time. No tails. Ever. That's the threshold for saying we discovered something. The gap between 3 sigma and 5 sigma isn't just math. It's telescope time. It's observations. It's years. To move from 99.7% confidence to 99.99994% confidence requires roughly 5 to 10 times more observation time than we've already spent. 5 to 10 times more windows where James Webb points at K2-18b instead of distant galaxies or forming stars or any of the thousands of other targets competing for its attention. The telescope has limited observation windows. It orbits 1,000,000 miles from Earth, balancing at a gravitational equilibrium point. It can only look at certain parts of the sky at certain times. Every hour spent on K2-18b is an hour not spent somewhere else. The gap between probably and definitely is more telescope time than it took to build the telescope in the first place. You might think this is gatekeeping. You might think scientists are being pedantic, overly cautious, holding back an announcement because they want perfect data in an imperfect universe. But they're not being cautious because they're afraid of being interesting. They're being cautious because they've been burned before. In 1996, scientists announced they'd found fossils of ancient Martian bacteria in a meteorite. The meteorite came from Mars. It landed in Antarctica. Inside it, researchers found microscopic structures that looked biological, tiny tubes, mineral deposits that, on Earth, only form in the presence of bacteria, organic molecules. The announcement made global headlines. The President of the United States held a press conference. We found life on Mars. Ancient life, dead life, but life. It was later retracted. The structures weren't fossils. They were mineral formations that happened to look biological. The organic molecules could have formed without biology. The whole thing fell apart under scrutiny. The announcement didn't just embarrass the researchers involved. It made the entire field more conservative, more careful, more demanding of proof before making claims. Because the cost of being wrong isn't just a correction in a scientific journal. It's credibility, it's funding, it's the public's trust in science. One false alarm about extraterrestrial life, and people stop listening when you find it for real. We could announce life on K2-18b tomorrow with 3 sigma certainty and be wrong. And that single mistake would set the search for extraterrestrial life back decades. Not years, decades. Because the next time someone detects a biosignature, even at 5 sigma certainty, the response will be, remember K2-18b, remember when they said they found life and they were wrong. The gap between 99.7% and 99.99994% is the gap between a headline and a legacy. This isn't about perfectionism, it's about responsibility. The current detection stands at 3 sigma. That's strong, that's worth investigating, that's worth more observations. But it's not enough to say, we found life. Not yet. To cross that threshold requires more data. More photons captured from K2-18b's atmosphere, more transits observed, more spectral lines analyzed. The work is ongoing. James Webb will return to this planet. Other telescopes will point at it. Ground-based observatories, future space missions. The data will accumulate. But here's what makes this complicated. While we're waiting for 5 sigma certainty on dimethyl sulfide, the telescope detected something else. Other molecules in that same atmosphere. Some expected, some not. And the combination of what's there and what isn't creates a picture that doesn't quite fit. A puzzle where the pieces almost lock together, but not entirely. Because K2-18b isn't just showing us one biosignature, it's showing us an entire atmospheric chemistry. And some of that chemistry raises new questions. The telescope detected methane in K2-18b's atmosphere, carbon dioxide, water vapor, all alongside that dimethyl sulfide that triggered the 99.7% calculation. Each molecule tells a story, but not all stories point in the same direction. Let's start with methane. Chemical formula CH4. 1 carbon atom bonded to 4 hydrogen atoms. On Earth, methane comes from 2 very different sources. Life makes it. Wetlands release it as organic matter decays. Livestock produce it in their digestive systems. Termites generate it by the millions of tons every year. But geology makes it too. Volcanic vents release methane from deep underground. A process called serpentinization produces it when water reacts with certain rocks. Methane in an atmosphere is like finding ash. It tells you there was a fire, but not whether it was a campfire or a forest burning. The presence of methane doesn't confirm life, it suggests the possibility. That's different. That's much more careful language. On Titan, Saturn's largest moon, the atmosphere is 1.4% methane. Titan has lakes of liquid methane on its surface, rivers of it carving channels through water ice. There's no life on Titan, at least none that we've detected. The methane there comes from geology, from chemistry happening in the absence of biology. K2-18b shows methane. That could mean microbes are producing it in vast quantities. Or it could mean the planet has active geology, volcanic activity, chemical reactions in a subsurface ocean. Without additional context, methane alone doesn't tell us which scenario we're looking at. Carbon dioxide appears in the spectrum too, CO2. 1 carbon, 2 oxygen atoms. We think of carbon dioxide as connected to life because we learned about photosynthesis in school. Plants take in CO2, release oxygen, grow. The air we breathe contains roughly 400 parts per million of carbon dioxide. Some of that comes from respiration, from animals breathing, from decomposition. But here's the thing that surprises most people. Carbon dioxide is actually one of the least useful molecules for detecting life. It's too common geologically. Venus has an atmosphere that's 96.5% carbon dioxide. The pressure at the surface is 92 times Earth's sea level pressure. The temperature reaches 467 degrees Celsius. That's hot enough to melt lead. Venus is completely dead. Mars has an atmosphere that's 95% carbon dioxide. Thin atmosphere. Cold. Probably dead. Detecting carbon dioxide on an exoplanet tells you almost nothing about whether life exists. Actually, that's not quite right. Let me try again. CO2 isn't a sign of life. It's just a sign of a planet with an atmosphere. On Earth, we associate it with life because plants use it. But that's backwards. Plants use it because it's abundant, not the other way around. The real biosignatures are the weird molecules, the ones that shouldn't be there unless something is making them on purpose. Carbon dioxide appears everywhere. It comes from volcanic outgassing, from impacts, from chemical weathering of rocks, from oceans releasing dissolved gas. It's ubiquitous. It's noise in the signal we're trying to isolate. Water vapor is different. H2O, hydrogen and oxygen. Water is essential for life as we know it. Every organism on Earth requires liquid water to function. Our cells are mostly water. Our biochemistry happens in water. Reactions that would take millions of years in a dry environment happen in milliseconds when water is present. Finding water vapor in an atmosphere matters. It suggests the possibility of liquid water on the surface or in clouds. It opens the door to chemistry complex, enough for life. But water vapor alone doesn't confirm anything. Venus has water vapor in its atmosphere. Trace amounts, but it's there. Jupiter has water vapor. Saturn, Uranus, Neptune. Water is common in the solar system. Ice covers moons throughout the outer planets. Comets are mostly ice. Water vapor is like finding a glass near a crime scene. It's interesting, but doesn't tell you if anyone was home. So we have methane, ambiguous. Could be life, could be geology. We have carbon dioxide, common everywhere, tells us almost nothing. We have water vapor, necessary for life, but present on dead worlds too. None of these molecules, taken individually, would justify a 99.7% confidence in biosignatures. But they're not appearing individually, they're appearing together, in combination. And that combination starts to narrow the possibilities. The atmosphere's chemical mix is like a recipe. Flour, eggs, and sugar could be cookies or cake. Both use the same basic ingredients. Add chocolate chips, and suddenly you know exactly what you're making. The presence of methane plus water plus dimethyl sulfide together creates a chemical profile that on Earth would indicate a thriving biosphere. Wetlands, ocean ecosystems, microbial mats covering shallow seas. The kind of environment where simple life doesn't just survive, but dominates. This is the pattern that matters. Not any single molecule, but the combination, the ratios, what's present and what's absent, what appears in quantities that make sense geologically versus what appears in quantities that only biology could explain. K2-18b shows all three supporting molecules in its atmosphere. Water that could support liquid oceans, methane that could come from microbes, carbon dioxide cycling through some kind of system, and threading through all of it, dimethyl sulfide, the molecule that shouldn't be there unless something alive is producing it. The inventory is almost complete. Almost. There are other molecules the telescope looked for and didn't find. Gases that would point more strongly toward geology. Gases that would suggest a runaway greenhouse effect like Venus. Their absence is as meaningful as the presence of what we did detect. But to understand why this particular combination of molecules matters so much, we need to look at the star. Because K2-18b doesn't orbit a star like our Sun. It orbits a red dwarf, and red dwarfs change everything about what we think we know regarding where life can survive. Red dwarfs are the smallest stars in the universe, the coolest, the dimmest, and by an overwhelming margin, the most common. About 75% of all stars in the Milky Way are red dwarfs. 3 out of every 4 points of light you could theoretically catalogue. That means in our galaxy alone, there are somewhere around 200 billion red dwarf stars. 200 billion. To put that in perspective, if you started counting one red dwarf per second, never stopping to eat or sleep, it would take you over 6,000 years to count them all. You'd start counting in the Bronze Age and finish sometime next millennium. K2-18b orbits one of these stars, a red dwarf with a surface temperature around 3,184 degrees Celsius. That sounds hot until you compare it to our Sun, which burns at 5,500 degrees. The difference matters. Red dwarfs burn cooler because they burn slower, much slower. They consume their hydrogen fuel at such a conservative rate that their lifespans stretch into the trillions of years. Not billions, trillions. The universe is 13.8 billion years old. That's ancient by any human measure. It's older than galaxies, older than most stars, older than planets and chemistry, and time itself as we understand it. But compared to the lifespan of a red dwarf, 13.8 billion years is nothing. It's a brief moment, an opening chapter. Here's the strange part. Not a single red dwarf has ever died. Every red dwarf born since the Big Bang is still burning today. Every single one. They formed when the first generation of matter coalesced into stars, back when the universe was young and hot and simple. And they're still here, still burning, still converting hydrogen into helium at a pace so gradual that the fuel will last for trillions of years to come. Think about that. Our Sun is about 4.5 billion years old. It has maybe 5 billion years left before it swells into a red giant and destroys the inner planets. If our Sun is a bonfire that will burn out in 10 billion years, red dwarfs are candles that will flicker for trillions. They'll outlive galaxies. They'll outlive the universe as we know it. This matters for one simple reason. Life needs time, complex life especially. It took Earth 4 billion years to go from single cells to something that could look up at the stars and wonder what they are. 4 billion years of false starts and extinctions and evolutionary dead ends. That's almost the entire lifespan of our Sun spent just getting to us. Red dwarfs offer trillions of years. That's not just more time, that's more chances. More opportunities for chemistry to stumble into biology. More rolls of the dice, and because red dwarfs are so common, the math shifts dramatically in their favor. Looking for life around sun-like stars is like searching for a needle in a haystack. Looking around red dwarfs is like searching in a haystack made of needles. There are simply more of them, more planets, more potential, more places where the conditions might be right. This is why K2-18b matters so much. It's not orbiting some rare stellar giant or exotic star system. It's orbiting the most common type of star there is. If we find life there, it suggests life might be everywhere, not scattered among the rare sun-like stars, but clustered around the billions upon billions of red dwarfs that fill the galaxy like grains of sand on an endless beach. The universe has only just begun by red dwarf standards. We live in the opening act, trillions of years from now, when every sun-like star has exploded or collapsed, when galaxies have drifted so far apart they can no longer see each other, when the universe is cold and dark and empty, red dwarfs will still be burning. They'll be the last stars left, the lonely campfires in an infinite empty desert, the last light in a dying cosmos. And if life exists around them now, those civilizations could survive for trillions of years, long enough to watch the universe itself grow old, long enough to see everything else fade into darkness while they remain. We might be searching for life that will outlive everything else that exists, life that will still be thriving when the last galaxy goes dark, when the final neutron star cools, when there's nothing left but those faint red embers and whatever clings to them. But red dwarfs come with a cost. They're not gentle hosts. They might burn for trillions of years, but they don't burn quietly. They flare, violently, unpredictably, blasting their planets with radiation that can strip away atmospheres and sterilize surfaces. K2-18b orbits one of these temperamental stars, and those flares could change everything about whether life can actually survive there. Stellar flares are how red dwarfs remind their planets who's in charge. They're violent, sudden, unpredictable, and for a planet like K2-18b orbiting so close to its star, they're a regular occurrence. Not something that happens once a century, not something rare and catastrophic like a solar storm on Earth. K2-18b receives a stellar flare every few hours to days. Imagine living somewhere. The sky erupts with the energy of 1,000,000 nuclear bombs while you sleep. That's not a metaphor. That's the reality of life in a red dwarf's habitable zone. A stellar flare is a sudden eruption of radiation and charged particles from a star's surface. It happens when magnetic field lines on the star get twisted, stressed, and then snap back into place. The energy release is instant, massive. The flare shoots out across space at nearly the speed of light, carrying X-rays, ultraviolet radiation, and a wave of charged particles that slam into anything in their path. If Earth got hit by one of the larger flares from K2-18b's star, the radiation would sterilize the surface in minutes. We'd be gone. Everything above ground would be cooked, and this happens to K2-18b constantly. The problem isn't just the radiation itself, it's what that radiation does over time. Stellar flares can strip away a planet's atmosphere if the planet doesn't have a strong magnetic field to protect it. Earth has a magnetic field, a powerful one. It deflects most of the charged particles the sun throws at us, funneling them toward the poles where they create auroras. But we don't know if K2-18b has a magnetic field. We can't measure that from here. If it doesn't, every flare peels away a little more of its atmosphere. Over millions of years, the planet could be left bare. Just rock and radiation. No air, no ocean, nothing. Even if K2-18b has kept its atmosphere, the flares create another problem. They mess with our measurements. When a stellar flare hits a planet's atmosphere, it can temporarily create molecules that look like biosignatures. Certain compounds form in the chaos of the radiation storm, then break apart when the storm passes. If we happen to observe the planet during a flare, we might detect those molecules and think they're signs of life, false positives, the universe playing tricks on us. This is one reason scientists are cautious about the dimethyl sulfide detection. It could be real, or it could be a ghost, a chemical shadow cast by a recent flare that will vanish when we look again. Stellar flares are like living next to a fireworks factory that explodes randomly. You might survive, but you'd need a very good shelter. Any life on K2-18b would have to deal with this. It couldn't live on the surface. Not permanently. The radiation from a stellar flare could sterilize Earth's surface in minutes. Life on K2-18b would need to hide underwater or underground, emerging only when the storm passes. Deep ocean life could survive, anything protected by meters of water or rock. But surface life, complex ecosystems exposed to open air, that's harder to imagine. The flares would be relentless. Here's the thing, we don't really know if stellar flares kill life or help it. That's the honest answer. We have theories, models, simulations, but we've never actually watched life evolve on a planet that gets hit by flares. We're guessing. Educated guessing, but guessing. Maybe life thrives in chaos. Maybe it needs the chaos. We won't know until we find it. Because there's a twist. Stellar flares might not be a deal breaker for life. They might actually be an advantage. When a flare hits a planet's atmosphere, it doesn't just bring destruction. It brings energy, lightning, lots of lightning. The charged particles slam into the atmosphere and create massive electrical discharges, storm after storm after storm. And lightning is one of the ways complex organic molecules form. This isn't speculation. We've known this since 1952, when a chemist named Stanley Miller ran an experiment that changed biology. He took a flask filled with water, methane, ammonia, and hydrogen, simple chemicals. Then he zapped it with electricity to simulate lightning. Within days, the flask was full of amino acids, the building blocks of proteins, the foundation of life. Planets around red dwarfs get bombarded by flare-induced lightning constantly, far more than Earth ever did, which means they might be better at creating the chemistry that leads to life, not worse. The violence isn't a bug, it's a feature. Every time K2-18b gets hit by a flare, its atmosphere lights up with electrical storms. Those storms create organic molecules. They rain down into the ocean. They accumulate. They combine. They build complexity. Life might thrive specifically because of the chaos, not despite it. Think about Earth in its early days. 4 billion years ago, the atmosphere was toxic. The surface was bombarded by asteroids. Lightning storms raged constantly, and somewhere in that violence, life began. We don't know exactly where or how, but we know the chaos helped. It provided the energy, the raw materials, the chemical reactions that built the first cells. K2-18b might be going through that same process right now, or maybe it already went through it billions of years ago, and whatever life emerged has adapted to the flares, evolved to use them, to hide when they come, and emerge when they pass. The flares make everything harder to study. They create noise in our data. They obscure the signals we're looking for. They force us to observe the planet multiple times across different wavelengths to separate the real biosignatures from the false ones. But they also make K2-18b more interesting, because if life exists there, it's not just surviving. It's surviving in conditions we'd consider impossible, thriving in a radiation storm, adapting to a star that tries to kill it every few hours. That's not fragile life clinging to existence. That's resilient life, tough life, life that found a way. So what kind of world could K2-18b actually be, given these challenges? So what kind of world is K2-18b actually? What kind of planet produces these chemical signals and survives this kind of radiation? There are two possibilities, two very different answers. And the difference between them is the difference between finding life and finding a clever illusion. The first possibility is called a Hycean world. The name comes from hydrogen and ocean. Picture a rocky core about the size of Earth, buried deep beneath a global water ocean that stretches down for hundreds of kilometers. That's deeper than Earth's oceans by a factor of 30. More water than all of Earth's seas combined, sitting atop that core. Above the ocean, a thick hydrogen atmosphere presses down with crushing force. The weight of that atmosphere is like standing a mile beneath Earth's ocean surface. The pressure never lets up. The water never ends. No land, no continents, no beaches. Just an endless dark sea under a dim red sky. These worlds might be the most common type of habitable planet in the galaxy, more common than Earth-like worlds with continents and shallow seas and breathable air. The surprise isn't that we found one. The surprise is that we exist on something different. Think about that for a second. We evolved on the weird planet, not the normal one. If you randomly selected a habitable planet in the Milky Way, it would probably be a Hycean world. Deep water, no land, crushing atmospheric pressure, a dim red sun that barely rises above the horizon. Earth-like worlds with blue skies and beaches might be the rarest habitable environments in the cosmos. We're the outliers. The aliens, if they exist, probably think their world is normal and would find Earth bizarre. A planet with so little water It has exposed rock, where the atmosphere is thin enough to see stars clearly, where you can stand on solid ground and breathe without being crushed. That's the strange one. The Hyson model fits K2-18b perfectly. The planet's mass and radius match. The hydrogen atmosphere explains the spectroscopic signatures. The ocean could be warm enough for liquid water, especially near the surface where the star's light penetrates. And deep beneath that surface, in the dark pressure of the abyss, life could thrive, protected from radiation, fed by volcanic vents. Adapting to conditions we'd find hostile but not impossible. That's Hypothesis 1, the optimistic scenario. Hypothesis 2 is darker, the magma ocean model. In this version, K2-18b is too hot. The surface isn't water, it's molten rock, a global sea of lava, churning and bubbling under that same thick atmosphere. The heat comes from tidal forces, from the star's radiation, from leftover energy from the planet's formation. The surface glows faintly red. Volcanic gases pour into the atmosphere. Hydrogen, methane, dimethyl sulfide, all the chemicals we thought were biosignatures. The difference between a Hyson world and a magma ocean is the difference between a swimming pool with a heater and a lava lamp. Both are liquid. Both produce gases, but only one is survivable. The magma ocean hypothesis explains the same data as the Hyson model. Same mass, same radius, same atmospheric composition, but it means everything we detected is a false positive. The planet is producing the chemical signals of life without any biology involved, just geology, just heat and pressure and volcanic activity mimicking the signatures we're searching for. No ocean, no life, just fire. The problem is that both models fit. The planet's size works for either scenario. A Hyson world with a deep ocean has a rocky core that gives it the right mass. A magma ocean world with a molten surface and thick atmosphere also matches. The chemicals we detected could come from biology or volcanism. The temperature could be warm enough for water or hot enough to melt rock. We can't tell from what we've measured so far. Trying to distinguish between them from 124 light-years away is like trying to determine if a distant light is a candle or a house fire by squinting. You see the glow, you know something is producing it, but the details are lost in the distance. So, which one is K2-18b? Are we looking at an ocean world where life might swim in the dark abyss? Or a hellscape that's tricking us into thinking we found something extraordinary? The honest answer is we don't know yet. Not for certain. The data we have is consistent with both scenarios. We need more information, more spectroscopic observations. We need to look for molecules that only appear in one scenario or the other, chemicals that can only form in liquid water, or gases that only emerge from molten rock. The distinction is everything. It's the difference between celebrating the discovery of a potentially habitable world and realizing we were fooled by volcanic activity. The next observations are already planned. More time with the James Webb Space Telescope, longer exposures, different wavelengths, looking for the specific signatures that will tell us which model is right. But those observations require precision. They require knowing exactly what to look for and how to measure it across a distance that defies comprehension. Which raises the question, how do you actually measure a planet 124 light-years away? The previous section asked how you measure a planet 124 light-years away. Here's the problem with that question. You don't measure it by going there. You can't go there. You will never go there. Neither will anyone you know. Neither will anyone they know. The distance to K2-18b isn't just far. It's a kind of far that erases the possibility of contact. Let's put a number to it. 124 light-years. That's about 730 trillion miles. Light itself, moving at 186,282 miles per second, takes 124 years to cross that gap. Light doesn't stop. Light doesn't slow down. Light is the fastest thing that exists, and it still takes more than a human lifetime to make the journey. What about us? What about something we've actually built? Our fastest spacecraft is Voyager 1. We launched it in 1977. It's been flying for nearly half a century. In that time, it's traveled about 15 billion miles. That sounds impressive until you do the math. At Voyager's speed of 38,000 miles per hour, reaching K2-18b would take 5.6 million years. That's longer than humans have existed as a species. You could launch Voyager when the first humans stood upright in Africa, and it would still be in transit today, with millions of years left to go. Maybe we could go faster. Let's imagine something wildly optimistic. A spacecraft that could travel at 1% the speed of light. That's about 6.7 million miles per hour. We cannot build this. We don't have the technology. We don't even have a theoretical design that could work. But let's pretend we do. At 1% light speed, the journey to K2-18b would take 12,400 years. That's longer than all of recorded human history, longer than the pyramids have stood, longer than any civilization has survived. You'd launch the mission, and your descendants wouldn't arrive until every language spoken today had died and been forgotten. What if you decided to walk 3 miles per hour, 1 foot in front of the other? The journey would take 27.6 trillion years. That's 2,000 times the current age of the universe. You could start walking the moment the Big Bang happened, never stop, never sleep, and you'd still have 99% of the journey left. The universe would end before you got there. Here's another way to see it. Imagine boarding a commercial airliner, cruising altitude, steady speed, 570 miles per hour. The flight to K2-18b would take 90 million years. You'd need to board the plane when dinosaurs ruled Earth, specifically during the late Cretaceous period. T-Rex would still be hunting. Triceratops would still be grazing. You'd sit in your seat, eating peanuts and watching in-flight movies, while the entire asteroid impact happens below you, while the dinosaurs die, while mammals rise, while primates evolve, while humans appear, build civilizations, invent flight itself, and you'd land tomorrow. The absurdity doesn't stop there. Let's say we crack physics in a way that seems impossible today. Let's say we build a ship that can travel at 99.9% the speed of light. Not light speed, but close enough that the difference barely matters. This is pure fantasy. The energy requirements alone would dwarf anything humanity has ever produced. But let's pretend. At 99.9% light speed, the journey would still take 124 years. You'd board the ship as a child. Your great-grandchildren would arrive as elders. There's a twist here that makes it even stranger. Time dilation. At 99.9% light speed, time slows down for the travelers. For you, on the ship, the subjective journey would feel like about 5.5 years. You'd age 5.5 years. You'd experience 5.5 years of boredom and wonder and waiting. Then you'd arrive. But back on Earth, 124 years would have passed. Everyone you knew would be dead. Your friends, your family, everyone you ever spoke to. The world you left would be gone. You'd step off the ship into a future you don't recognize, to meet the distant descendants of people you once loved. There is no loophole. There is no shortcut. The distance isn't just far. It's civilizationally unbridgeable. This is what we're actually talking about when we say we found potential life on K2-18b. We're not talking about a place we might visit someday. We're not talking about sending a probe in our lifetimes, or our children's lifetimes, or the lifetimes of anyone connected to us by memory. We're talking about a world we will only ever know through light, through the specific colors absorbed and emitted by its atmosphere, through spectroscopy and mathematics and inference. If we confirm life on K2-18b, we will never meet it. We will never touch it. We will never see it with our own eyes. We will only ever read its signature in starlight, a pattern of molecules, a chemical fingerprint that says something is alive 124 years in the past, because the light we're seeing now left that planet in the year 1900. While we watch today, that world has already moved on. Whatever is happening there right now, we won't know about it until the next century. The discovery wouldn't be a doorway. It would be a message in a bottle, floating across an ocean we cannot cross. We would know we're not alone. We would know life exists beyond Earth, but we would never shake its hand. We would never hear its voice. The gap is permanent. That's the reality of interstellar distance. It doesn't just separate us from other worlds. It isolates us, absolutely. Let's try counting backward. 124 years ago, it was the year 1900. The Wright brothers had not yet flown. World War I had not started. Antibiotics did not exist. The oldest person alive today was not yet born. That's how long the light from K 2-18b has been traveling. Not ancient history, not deep time, just barely beyond living memory. If you counted backward 1 year at a time, starting today, you'd reach 1900 in just over 2 minutes. 1, 2, 3, keep going. 124 seconds. That's nothing. But if you counted 1 light year per second, trying to measure the distance to K 2-18b, something strange would happen. In the time it took you to count to 124, the light from that planet would have traveled another 124 light years. You'd be further behind than when you started. You could count forever and never catch up. The gap would only widen. Think about what 124 years means for a human life. Every person has roughly 128 generations of ancestors going back to the origin of agriculture. 124 is nearly that entire span of lineage. Every birth, every death, every life lived between the first farmers and you. That's the depth of time we're talking about. Not cosmic, not geological, just barely beyond the edge of what humans can remember through stories. The light we detected didn't just carry an image of K 2-18b. It carried every moment of its 124-year journey. Photons don't experience time. To them, the trip is instantaneous, but the space they crossed does. That light passed through clouds of interstellar dust. It skirted the edges of stellar nurseries. It crossed the voids between spiral arms. 730 trillion miles of empty space, and it survived. Any debris in its path would have absorbed it. Any gravitational lens could have bent it away from Earth. The fact that it arrived at all is a statistical miracle. It threaded the needle across the galaxy to hit a 21-foot mirror in exactly the right way. We didn't just detect dimethyl sulfide on another world. We caught ghosts that almost didn't make it. Do you ever think about the light that doesn't make it? The photons that left K 2-18b the same moment as the ones we detected, but got absorbed by a speck of dust 1,000 light years from Earth? They traveled for 123,999 years and then just stopped, ended. One atom away from being part of the most important discovery in human history. How many biosignatures have we missed? Not because life doesn't exist, but because the light just didn't make it. If you could count 1 star per second in all the space between us and K 2-18b, you'd count for 200,000 years without sleep and still not finish. That's not because the stars are dense. It's because the space is so vast that even scattered stars add up to numbers we can't comprehend. Every point of light between here and there represents a system we'll likely never visit, a volume of space we'll never cross. Light from K 2-18b left when Beethoven was composing his 9th Symphony. 1824. He was deaf by then, conducting from memory and intuition, writing music he could only hear in his mind. That cosmic note has been traveling ever since. We're just now hearing it. 124 years for light to cross the gap, 199 years since it left. The signal has been coming this whole time. We just weren't listening yet. Every breath you take contains atoms that were once inside a star. You're not separate from the cosmos. You're made of its recycled pieces. The carbon in your cells, the calcium in your bones, the iron in your blood. All of it forged in stellar furnaces billions of years ago. Stars died so you could exist. Their light scattered. Their matter drifted through space and eventually collapsed into new systems, new planets, new life. The light carrying potential evidence of life from K 2-18b is no different. It's just photons, just electromagnetic radiation. But it's also a message, a signal that crossed more than a century of space to reach us. It left that planet before anyone alive today was born. It traveled while empires rose and fell. while we invented flight and split the atom and walked on the moon. It was always coming. We just had to build the instrument sensitive enough to catch it. That's what James Webb is, a net for ancient light, a 21-foot mirror floating 1,000,000 miles from Earth, catching photons that left distant worlds before our grandparents were born. The telescope doesn't create discoveries. It just reveals what's already there, what's always been there, signals crossing the void, waiting for someone to notice. We talk about finding life on other worlds like it's something we do, like it's an achievement, but the life was already there. The signal was already traveling. We didn't create the discovery. We just finally looked in the right direction, at the right time, with the right tools. The universe has been broadcasting this whole time. We're only now learning to tune in. The telescope doesn't see the planet. That's the first thing you need to understand. James Webb isn't looking at K2-18b directly. It can't. The planet is too small, too dim, too close to its star. The star outshines it by a factor of millions. Trying to see the planet next to its star would be like trying to spot a firefly hovering next to a stadium floodlight from across the country. It's not possible. Not with current technology, not even with James Webb. What the telescope sees is the star, just the star, and it watches what happens when the planet passes in front of it. Every 33 days, K2-18b crosses between its star and us. This is called a transit. The planet blocks a tiny fraction of the star's light, about 0.15%. If the star were a light bulb in your hand, the planet would dim it by an amount you couldn't detect with your naked eye. But James Webb can measure that dimming, and more importantly, it can measure how that dimmed light changes color. Here's where transmission spectroscopy comes in. When starlight passes through the planet's atmosphere on its way to us, molecules in that atmosphere absorb specific wavelengths. Different molecules absorb different colors. Methane absorbs certain wavelengths in the infrared. Water vapor absorbs others. Carbon dioxide has its own pattern. Each molecule leaves a unique fingerprint in the spectrum, a specific set of dark lines where it grabbed photons out of the light stream. Think of it like this. The telescope is reading a label on a test tube, but the test tube is thinner than a human hair, and it's being read from Mars. That's transmission spectroscopy. You're analyzing an atmosphere you can't see, around a planet you can't photograph, by measuring how it changes light from a star 124 light-years away. The signal is absurdly faint. The planet blocks less than 0.2% of starlight during a transit. The atmospheric absorption is a tiny fraction of that tiny fraction. We're measuring a change in brightness of maybe a few parts per million. If you dimmed a light bulb in your living room by that amount, you'd never notice. Every atom in the universe would have to conspire against you for your eye to catch it, but James Webb caught it. The telescope observed K2-18b for approximately 60 hours total, not all at once, across multiple transits, multiple passes, collecting photons one by one. If those photons were rain, we caught enough to wet a fingertip and declared we understand an entire ocean. That's the scale we're working with. That's the confidence we're building entire theories on. The Webb telescope focuses on infrared light specifically, wavelengths between about 3.3 and 9.1 micrometers. That's where many atmospheric molecules reveal themselves. That's where methane shows up, where water vapor becomes visible, where carbon dioxide draws its signature, and where dimethyl sulfide, if it exists, leaves its mark. Finding DMS in that spectrum is like hearing a single whispered word in a stadium full of people shouting. You need perfect silence, perfect listening, perfect conditions. The molecule's absorption lines overlap with other signals. Methane absorbs nearby wavelengths. Water vapor creates interference. You have to separate one whisper from 1,000 shouts and be certain you heard it correctly. We've never actually seen K2-18b. We've never photographed it, never captured an image. We only know it exists because it blocks a fraction of a percent of light every 33 days. Everything we know about this planet comes from measuring how that blocked light changes color, its size, its mass, its atmospheric composition, the potential for life, all of it derived from shadows and spectral lines. The light we're analyzing left the planet in 1900. It traveled through space while the Wright brothers flew at Kitty Hawk, while Einstein published relativity, while we invented television and computers and walked on the moon. The light was always coming, always carrying information. We just had to wait for it to arrive and build an instrument sensitive enough to read it. That's what makes this so strange. We're declaring the possibility of alien life based on data we've never directly observed, only inferred, only calculated from its effect on something else. It's like declaring someone exists because you saw their shadow on a wall, and from that shadow, you deduced their height, their weight, what they had for breakfast, the exact chemical composition of their breath. But that's all we have. That's all we'll ever have until we build bigger telescopes or faster spacecraft. Shadows and spectra, colors in ancient light, absorption lines in infrared wavelengths. We're reading labels from across the cosmos on test tubes we can't see, analyzing atmospheres around planets we can't photograph, searching for life we can't touch. And somehow, impossibly, it works. The math adds up. The molecules reveal themselves. The signatures match. We can tell you what's in an atmosphere 124 light years away with enough confidence to publish papers and make predictions. We can detect dimethyl sulfide in concentrations of parts per billion in an atmosphere we've never sampled. We can do this because light carries information, because molecules absorb specific wavelengths, because physics works the same everywhere. But DMS isn't the only molecule in that atmosphere. The spectrum shows other signatures, other fingerprints, some expected, some less so. And those other molecules complicate the picture in ways that challenge the simple story of life. The search for life beyond Earth has a problem. It's not that we haven't found anything. It's that we keep finding things that look like life, but aren't. False alarms, dead ends, promising signals that evaporate under scrutiny. The history of biosignature detection is mostly a history of almost, but not quite. Searching for life through spectroscopy is like being a doctor who can only diagnose patients by smelling their breath from across a football field. You might catch something. A whiff of acetone suggesting diabetes. A hint of ammonia indicating kidney failure. But you'll have a lot of false alarms. Someone ate garlic. Someone drank coffee. Someone used mouthwash. The signal you're detecting is real, but the diagnosis is wrong. That's where we are with exoplanet atmospheres. We detect molecules from 100 light years away and try to diagnose what made them. Sometimes we get it spectacularly wrong. Take Venus. In 2020, scientists announced they'd detected phosphine in the Venusian atmosphere. Phosphine is a molecule made of phosphorus and hydrogen. On Earth, it's produced by anaerobic bacteria, microbes living in oxygen-free environments, swamps, guts, sewage treatment plants. Finding it on Venus was shocking because Venus is a hellscape where lead melts on the surface. If phosphine was there, something was making it, something that might be alive. The announcement made headlines worldwide. Life on Venus, our neighbor, the planet next door. The scientific community erupted with excitement and skepticism in equal measure. Teams rushed to reanalyze the data. They looked at the same spectral lines, the same absorption features, the same wavelengths of light passing through Venus's clouds. The signal fell apart. Some teams found the phosphine signature was contaminated by sulfur dioxide instead. Others suggested the original analysis had processing errors. The molecule might not be there at all, or, if it is there, it's in concentrations far too low to require biology. Volcanic activity could produce it. Lightning in the clouds. Chemical reactions we haven't thought of yet. The phosphine might be real. The life is probably not. That's the frustrating part. The most frustrating thing about false positives isn't that they're wrong. It's that they're usually correct about the molecule, but wrong about the source. There really is methane on Mars. There might actually be phosphine on Venus. The molecules are there. The false part is assuming they come from life when they might not. We're not dealing with measurement errors or bad data. We're dealing with ambiguous chemistry. The universe is full of ways to make the same molecule, and we're trying to figure out which factory produced it without ever visiting the factory. Mars has been teasing us for decades. Rovers on the surface detect seasonal methane plumes. Concentrations rise and fall with the Martian year. On Earth, 95% of atmospheric methane comes from biology: bacteria in wetlands, livestock, rice paddies, termites. Life produces methane as a waste product of metabolism. Finding it on Mars should mean something. Except geology also makes methane. Serpentinization, water reacting with iron-rich rocks, volcanic outgassing, ancient methane trapped in ice that melts and releases during summer. We've been detecting these plumes since 2003, and we still don't know what makes them. Every potential biosignature is Schrödinger's alien, simultaneously life and not life, until you gather enough data to collapse the uncertainty. Titan is even more confusing. Saturn's largest moon has an atmosphere thicker than Earth's. It's full of organic chemistry. Hydrocarbons rain from the sky. Methane lakes pool on the surface. Ethane, propane, nitriles, complex molecules containing carbon, hydrogen, and nitrogen. The building blocks of life. All the ingredients are there. None of it is alive. Titan's organic chemistry comes from photochemistry, sunlight hitting methane in the upper atmosphere, breaking it apart, reassembling it into more complex forms. The molecules rain down, they pool, they flow in rivers and collect in seas. It looks like biology. It's just physics and chemistry happening without any living thing involved. The universe can be deceptive that way. Europa and Enceladus have subsurface oceans, water under ice shells, hydrothermal vents on their seafloors. On Earth, hydrothermal vents teem with life, tube worms, bacteria, entire ecosystems that never see sunlight, energy from chemical reactions instead of photosynthesis. If life exists anywhere else in our solar system, those moons are the best candidates. We have no confirmed biosignatures from either one. Water plumes erupting from Enceladus contain organic molecules, but nothing that requires biology. Europa's ice shows surface chemistry consistent with a salty ocean below, but no smoking gun, no phosphine, no unexplained methane, no dimethyl sulfide, just water and salt and the faint possibility of something more. There's a running joke in the astrobiology community. We've discovered life on Mars 17 times, and it's died every time we got more data. It's funny because it's painful. Every generation of scientists thinks they're the ones who finally got it right, and every generation gets humbled by the next dataset. Maybe K2-18b is different. Maybe this time we really did find it. Or maybe in 10 years there will be a quiet retraction in a journal nobody reads, and we'll move on to the next candidate. That's the game. You keep looking, keep hoping, and keep getting disappointed until one day you're not. The search for life is a graveyard of this could be at moments that turned into never mind footnotes. Viking landers in the 1970s conducted experiments that detected metabolic activity in Martian soil. The results were positive. Then they realized the chemistry could happen without biology. The Allen Hills meteorite in 1996 showed structures that looked like fossilized bacteria. They probably weren't. Exoplanet after exoplanet shows water vapor, and we get excited, and then we remember, water alone doesn't mean life. K2-18b might really have DMS, and we might still be wrong about what it means. That's the reality we're dealing with, not bad science, not faulty instruments, just the enormous difficulty of reading chemistry from across the void and knowing what story it tells. The molecules don't lie, but they don't explain themselves either. We have to guess, and sometimes we guess wrong. That's why the 99.7% confidence matters. That's why scientists are cautious, because they've been burned before. The question isn't whether K2-18b has dimethyl sulfide. The question is what happens if we're right this time? What happens if we're right this time? That's the question we need to sit with, not the chemistry, not the detection methods, not even the probability. The question is what it means for humanity if we confirm that something alive exists on K2-18b. What changes? What breaks? What becomes possible? Let's start with the most immediate implication. If K2-18b has life, then life is common in the universe. Not rare, not special, common. That's what the statistics tell us. We've been searching for biosignatures on exoplanets for less than 20 years. K2-18b is 124 light-years away. That's our neighborhood. That's the equivalent of finding something in your front yard. If we find life this close, this soon, on one of the first Hycean worlds we properly examined, then the universe is full of it. Everywhere. Think about what that means. We didn't search a million worlds. We didn't scan every star system in the galaxy. We looked at a handful of planets with the right conditions, and we might have already found one with life. That's like scooping a cup of seawater from the ocean and finding a fish on your first try. You don't conclude that fish are rare. You conclude the ocean is teeming with them. The Drake equation tries to estimate how many intelligent civilizations exist in the Milky Way. The numbers range wildly depending on your assumptions. Conservative estimates say maybe 1,000. Optimistic ones push it to 100 million. Those calculations depend on one critical variable. How often does life actually arise when the conditions are right? We've had no data for that variable. It's been a complete guess. Confirming microbial life on K2-18b would give us our first real answer, and it would push every estimate upward. If life arose independently on a world that different from Earth, then the chemistry that leads to biology isn't picky. It happens when it can. It also means life doesn't need Earth. It doesn't need our exact temperature range, our exact atmospheric composition, our exact orbit. K2-18b is a mini Neptune with a hydrogen-rich atmosphere and crushing pressures, and an ocean that might exist under conditions we'd consider hostile. If life is there, it means biology is flexible, adaptive, resilient. It means the universe has been running experiments in chemistry for billions of years, and those experiments succeed more often than we thought. Here's the scale we're talking about. There are 2 trillion galaxies in the observable universe. Each galaxy has hundreds of billions of stars. Most of those stars have planets. If life arose on K2-18b, then we are not the only chemistry that woke up. We're not the only molecules that started asking questions. Somewhere in that 2 trillion galaxy expanse, other things are alive. Maybe billions of them, maybe trillions. We'd go from being alone to being one voice in a chorus so vast we can't even comprehend the number. That's not just a scientific discovery. That's a philosophical earthquake. Every religion, every cultural story, every assumption we've built about our place in the universe gets rewritten. Some faiths would adapt easily. Life on other worlds doesn't contradict most religious texts, but it changes the framing. Earth stops being the center. Humanity stops being the only experiment. We become one branch on a tree with roots we can't see and branches stretching farther than we can imagine. The psychological impact is harder to predict. Some people would feel smaller, less significant. If life is common, then we're not special. We're just another instance of chemistry getting complicated. Others would feel connected. We're part of something larger, a universe where biology emerges whenever it gets the chance. A cosmos designed, or at least predisposed, to create life. Both reactions are valid. Both would coexist. The discovery wouldn't unite humanity in some grand moment of clarity. It would fracture us into 1,000 interpretations of what it means. But here's what would remain true, regardless of interpretation. If K2-18b has life, it's been living and dying and evolving, while every photon carrying that news crawled through 124 light-years of void to reach us. The organisms there, if they exist, have no idea we're watching. They've been metabolizing, reproducing, adapting for however long they've existed. And we're only just now noticing. The light we're analyzing left that planet during the early 19th century. Whatever's happening there now, we won't see for another century. We're always looking at the past. Here's the other certainty. We'll probably never meet them. K2-18b is close by cosmic standards. It's impossibly far by human ones. 124 light-years means 124 years traveling at the speed of light. We can't travel at the speed of light. Our fastest spacecraft would take hundreds of thousands of years to get there. Even if we developed technology 1,000 times faster, it's still a journey measured in centuries. Confirming life on K2-18b would be like finding one ant in your backyard and realizing Your property is built on an anthill that covers the continent. You know it's there. You know it's vast, but you'll never walk to the other side. That's the strange duality of this discovery. It would tell us we're not alone, and it would confirm we're still isolated. Life could be everywhere, and we'd still be trapped in our corner of the galaxy, knowing but never touching. There's something else we need to talk about. The way we'd confirm life on K2-18b. It won't be because they sent us a message. It won't be because they built megastructures, or visited Earth, or transmitted signals. It will be because they polluted their atmosphere. The way we'll announce we're not alone in the universe is by detecting waste products, metabolic byproducts, chemical exhaust, the molecular equivalent of garbage. Dimethyl sulfide isn't a message. It's not intentional. It's just what living things release because those molecules are useless to the organism that made them. Life's signature isn't art or technology or philosophy. It's burps and farts, molecules floating in the atmosphere because some microbe didn't need them anymore. The most profound discovery in human history will be announced with a straight face by scientists who say, "We detected biological waste gases." That's it. That's the headline. We found alien garbage floating in the sky. And from that garbage, we concluded we are not alone. There's something oddly perfect about that. We're not looking for aliens because we expect them to be rare. We're looking because if they're common, that changes what it means to be human. It changes our place in the story. And the evidence for that won't come from intention or intelligence. It will come from the ordinary, mundane process of life doing what life does. Eating, metabolizing, excreting, surviving. If we confirm life on K2-18b, the universe doesn't become more welcoming. It just becomes more populated. We're still alone in practical terms, still isolated by distance. But the loneliness shifts. It's not the loneliness of being the only ones. It's the loneliness of knowing others exist and never being able to reach them. That might be harder to live with, but before we wrestle with those implications, we need to answer one more question. Are we actually right this time? Because confidence isn't certainty. 99.7% isn't 100. And there's still work to be done before anyone declares this case closed. Moving from 99.7% confident to 99.9999% confident doesn't just require more data. It requires a lot more data. 5 to 10 times as much observation time. That translates to somewhere between 300 and 600 additional hours of James Webb Space Telescope time pointed at K2-18b. 300 to 600 hours. That's roughly 12 to 25 full days of continuous observation. Not consecutive days, of course. The planet has to be in the right position. Earth has to be in the right position. The telescope has to be scheduled. 3 sigma to 5 sigma sounds like a small step. It's not. It's years of waiting for a machine to stare at a single dot of light long enough to be absolutely sure. The challenge isn't just time. It's competing priorities. The James Webb Space Telescope cost $10 billion and took 25 years to build. It has enough fuel to operate for about 20 years total. Every hour spent observing K2-18b is an hour not spent observing the early universe, or distant galaxies, or other exoplanets. There are scientists whose entire careers depend on getting telescope time, and they're all competing with the "maybe we found aliens" team for resources. Waiting for telescope time is like waiting for a single parking spot in a city of 1 million cars. Everyone needs it. You're not the only one in line, and the person deciding who gets the spot has to balance the needs of everyone waiting. The decision of how much time to dedicate to K2-18b is both scientific and political. How much should we bet on one planet when there are thousands of other targets? How much weight do you give to the possibility of confirming life versus the certainty of learning something about galaxy formation? The answer to "are we alone" might come down to a committee meeting about scheduling. That's not a flaw in the system. That's just reality. Resources are finite, even when the resource is the most advanced telescope ever built. K2-18b transits its star every 33 days. That gives us regular observation windows. Every 33 days, the planet passes in front of its star from our perspective. Every 33 days, we have a chance to collect more data. That sounds frequent. It's not. The planet has to be positioned correctly relative to Earth. The telescope has to be available. The observation has to be scheduled months or years in advance. Each transit gives us a few hours of usable data. To accumulate 300 to 600 hours, we need dozens of transits, dozens of perfectly timed windows, dozens of opportunities where nothing goes wrong. Even with all that time, scientists aren't just collecting more of the same data. They need to observe at different wavelengths to rule out contamination from other molecules or stellar activity. They need to confirm that what looks like dimethyl sulfide isn't actually something else mimicking its signature. They need to check for ammonia or nitrous oxide or other biosignature molecules that might strengthen the case. They need to observe the star itself to make sure it's not producing signals that could be mistaken for atmospheric chemistry. Every alternative explanation has to be tested. Every possibility has to be ruled out. That's what 5 sigma means. Not just more confidence, more completeness. The timeline for confirmation depends on how aggressively the committee allocates telescope time. Optimistically, 2 to 3 years. Realistically, 5 to 10 years. Maybe longer. That's assuming everything goes right. Assuming the telescope keeps operating. Assuming no technical failures. Assuming no new priorities arise that push K2-18b down the list. 5 to 10 years. That's a graduate student's entire PhD. That's a career milestone delayed. That's a generation of scientists waiting to know if their hunch was correct. We might confirm alien life not with a radio message or a flying saucer, but with a spreadsheet showing molecular absorption lines, rows and columns of numbers, statistical significance climbing from 3 sigma to 4 sigma to 5 sigma. No dramatic reveal, no moment of contact, just data accumulating slowly until the case becomes airtight. The gap between probably life and definitely life is measured in years of waiting for machines to stare at a single dot of light long enough to be sure. The waiting game isn't passive. Scientists are already planning, proposing observation schedules, writing proposals for telescope time, arguing their case to review committees, building models to predict what they should see if life is really there, preparing for the possibility that they're wrong, preparing for the possibility that they're right. The work doesn't stop just because the initial results are promising. If anything, it intensifies. The stakes are higher now. The scrutiny is sharper. Everyone is watching. And while we wait, K2-18b keeps orbiting its star. Every 33 days, it crosses in front. Every 33 days, starlight filters through its atmosphere. The molecules are still there. The signal is still there, whether we're looking or not, whether we've confirmed it or not. The planet doesn't care about our timelines or our committee meetings or our bureaucracy. It just exists, doing what it does, reflecting light, absorbing wavelengths, carrying whatever secrets are hidden in that thick hydrogen envelope. The question isn't just whether we're right about K2-18b, it's whether K2-18b is unique or common. If life can arise on a planet like this, how many others are out there? How many Haitian worlds orbit in how many red dwarf stars? The universe has billions of candidates. K2-18b is just the first one we looked at closely enough to see something interesting. If it turns out we're right, the floodgates open. If we're wrong, we keep searching. Either way, we've learned where to look. We've learned where to look, and when we look, we find oceans everywhere. As of 2024, astronomers have confirmed over 5,500 exoplanets, 5,500 worlds orbiting other stars. That's more planets than most people will visit cities in their lifetime. Each one is a data point. Each one tells us something about how planets form, what they're made of, whether they could support life. Out of those 5,500, about 50 to 100 sit in their star's habitable zone, the Goldilocks region. Not too hot, not too cold, where liquid water could exist on the surface if conditions are right. 50 to 100 doesn't sound like much. But here's the thing, those numbers only reflect the planets we've found, the ones bright enough, close enough, positioned just right for our telescopes to detect. We've surveyed maybe 0.1% of the stars in our galaxy. We're not even scratching the surface. We're tapping it with a feather. And among those confirmed worlds, a pattern is emerging. Hycean planets might represent 10 to 30% of all exoplanets, maybe more. Mini Neptunes with thick hydrogen atmospheres and liquid water oceans underneath. They're not rare, they're not special. They might be the most common type of habitable world in the universe. Think about that. Ocean worlds might be the most common habitable planets in the galaxy, yet we evolved on the rarest type, a dry rock with just enough water. Earth is the exception, not the rule. We spent our entire history assuming life would look like us, arise like us, need what we need. We built our search around planets that resemble home, but home might be the oddball, the outlier, the weird one. K2-18b is the first Hycean candidate with a potential biosignature, but it's not alone. There are at least a dozen other similar candidates within 150 light-years. Planets we've catalogued but haven't studied yet. Planets with the right size, the right temperature, the right atmospheric signals to make them worth a closer look. Some are closer to Earth than K2-18b. Some orbit quieter stars, stars that don't flare as violently. Some have thicker atmospheres that would be easier to analyze, clearer signals, better data. We picked K2-18b partly because it transits frequently and is bright enough to study, not because it's the most likely to have life. We chose it because it was convenient, because the geometry worked out, because we could actually get good data from it with the tools we have. The most habitable planet in the galaxy might be one we haven't discovered yet, or one we've catalogued but haven't had time to study. A name in a database somewhere, waiting its turn. The announcement of life might not come from K2-18b at all. It might come from a planet we don't even know about yet, discovered by a telescope that hasn't been built, analyzed by scientists who are still in graduate school. We're racing to confirm something that might already be obsolete. By the time we definitively prove life on K2-18b, if we ever do, there might be 10 other candidates with stronger signals, better data, more compelling evidence. There's something darkly funny about spending billions of dollars and decades of human effort to study one planet, knowing full well that next year someone might find a better candidate and make all this work feel quaint. It's like building a cathedral to honor the first bird you ever saw, and then realizing there are billions of birds. The search for life isn't a single question. It's an infinite series of questions, each one slightly better than the last. K2-18b is just the one we're asking right now. Searching 5,500 exoplanets for life is like reading the first page of the first book in a library of 1,000,000 volumes. We've barely started the introduction. The table of contents is still unfolding. Every new planet we find adds another page, another chapter, another volume to the collection. The library keeps growing faster than we can read it. The Milky Way likely contains 40 billion Earth-sized planets in habitable zones. 40 billion. That's more than 5 planets for every person alive today. And that's just the Earth-sized ones. If you include Hycean worlds, mini Neptunes, super-Earths, all the planets that might have liquid water somewhere in their structure, the number climbs into the trillions. Trillions of worlds where life could theoretically arise, where chemistry could become biology, where something could look up at the stars and wonder if it's alone. If every star in the Milky Way had one Hycean world, and 1 in 1,000,000 had life, there would still be 100,000 biospheres in our galaxy alone. 100,000 planets where something swims, something metabolizes, something reproduces. 100,000 experiments in what life can be. And that's a conservative estimate. That's assuming life is rare, difficult, unlikely. If life turns out to be easy, if it arises whenever conditions allow, the numbers become absurd. Millions of living worlds, tens of millions, all of them doing their thing, evolving, adapting, surviving. We've barely begun to search. K2-18b is one planet, one atmosphere, one set of molecules filtered through starlight. It's the first domino, maybe, or it's a false start. Either way, it's not the last word. It's barely the first syllable. The galaxy is full of oceans, full of atmospheres, full of chemistry we don't understand yet, full of possibilities we haven't imagined. K2-18b showed us where to look. Now we have to look everywhere else. For most of human history, we've stared up at the night sky and asked the same question. Are we alone? Thousands of years, millions of people, all wondering, never knowing. The philosophers asked it. The poets asked it. Your ancestors asked it standing in fields under stars, so thick they looked like clouds. They had no way to answer. No tools, no method. Just the question, hanging there in the dark, generation after generation. We're different. We're the first generation with the actual capability to find out, not to guess, not to philosophize, to measure, to detect, to confirm. We built telescopes that can taste the air of planets 40 light-years away. We built sensors that can catch individual photons that have been traveling since before humans learned to write. We built models that can predict what life smells like on a world we'll never visit. Every generation before ours lived in a universe where aliens were purely philosophical. We might be the first generation for whom they're just chemistry. Think about what that means. Your great-great-grandparents couldn't have known. Your grandparents couldn't have known. Your parents grew up in a world where the question was still unanswerable. But you might live to see the answer. Not maybe, not someday in the distant future. Actually, live to see it. The announcement could come next year, or in 5 years, or 20. But it's coming. The tools exist. The searches are running. The data is accumulating. We're standing in the narrow slice of history between ignorance and knowledge, between wondering and knowing. That's where we are right now. K2-18b might be the answer, or it might not be. The data is tantalizing, but it's not conclusive. Not yet. We need more observations, more spectra, more time with Webb's instruments pointed at that one pale dot. The certainty might climb from 99.7% to something undeniable, or it might collapse as new data reveals a simpler explanation. That's how science works. That's how it should work. The universe doesn't owe us easy answers. If K2-18b does have life, though, everything changes. Not just because we found life, but because of what it means to find it this close, this soon. If the first world we properly investigate turns out to be inhabited, that tells us something profound. It means life isn't rare. It isn't special. It isn't a miracle that happened once and never again. If we found it within 40 light-years, on one of the first dozen planets we looked at carefully, it means the universe is full of it. Absolutely full. Billions of living worlds, most of them doing their thing in silence, unaware of each other, just existing, metabolizing, reproducing, evolving. We'd have our answer, and the answer would be, you were never alone. Not for a second. You just couldn't see your neighbors yet. And here's the thing nobody talks about. The moment we confirm life on another world, everything will change and nothing will change. The sun will still rise. You'll still go to work. Your coffee will taste the same. The news will announce it. People will talk about it for a week, and then it will fade into background knowledge, the way the moon landing did, the way every profound discovery eventually does. We'll have rewritten our place in the universe, and most people will shrug and move on. That's not cynicism. That's just how humans work. We adapt to miracles. We get used to the impossible. The announcement will probably happen in a peer-reviewed journal with a title so technical that most people will scroll past it. The most important sentence ever written, buried in a PDF. And maybe that's okay. Maybe the point isn't that we found life. It's that we looked, that we cared enough to spend centuries wondering, and decades building machines to check. The answer matters less than the asking. We might not get confirmation from K2-18b. We might have to wait for the next Hyson world, or the one after that. We might have to wait for a better telescope, one that hasn't been built yet, one that won't launch for another 20 years. The answer might come when you're old, or it might not come in your lifetime at all. It might be your grandchildren who hear it first, scrolling through news on a device you can't imagine, reading a headline you dreamed about. That light is still traveling toward us, from K2-18b, from 1,000 other worlds, carrying messages we haven't decoded yet. information we haven't captured, answers we haven't earned. The search continues. The instruments keep watching. The scientists keep analyzing. Somewhere in the data we've already collected, or in the data we'll collect next year, the answer might be waiting, already there, already true, just not seen yet. We're the generation that started asking with tools instead of just wonder. Whether we're also the generation that hears the answer, we'll see. Either way, we looked, we built the machines, we pointed them at the sky, we tried, and maybe, just maybe, the universe is about to whisper back